So today we're going to be having a look at confidence intervals. So if you have some data from an experiment or survey, then we can find its mean. This mean will not be the same as the real mean being the mean of the entire population. But if the sample that we have taken is good enough, then it should be quite close to the actual mean, the mean of the population. A confidence interval is a way of giving us some wiggle room when we know roughly what an average is, but not exactly what the population average is. We have a few different circumstances which we need to take into account. If we know or do not know the population standard deviation, and if we have a large or a small sample. Now, some of this we've talked about before in AS when we were looking at hypothesis testing with the normal distribution. In AS, we had a look at large samples, either when we knew the population standard deviation or we didn't know the population standard deviation. Remember that in this circumstance where we didn't know the population standard deviation, but instead we had a sample standard deviation, because the sample is a large sample, we can assume that the sample standard deviation is close to the population standard deviation. And the third circumstance that we're going to look at the moment is where we have a small sample and a known standard deviation. And the reason why we're looking at these three is because, as you can see from this table, they all mean that we are looking at the same test. We can see here that in each of these three circumstances, we have a normal or Z that we are looking at. There is a second test, and this is when we have a small sample and we have an unknown population standard deviation. Now, the issue that we have here is because the sample is small, we cannot assume that the sample standard deviation is going to be close to the population standard deviation. So that means that instead we have to do a different test, which is called T. And we are going to come on to looking at this a little bit later on. But for now, we are going to be focusing on the large sample, known and unknown standard deviation, and the small sample, known population standard deviation. So to start off with, as I was just saying, we're going to have a look at the large sample, known and unknown standard deviation. If we use a large amount of data, then no matter whether we are given the population or the sample standard deviation, if the sample is large, meaning that we have greater than or equal to 30 pieces of data, then we can assume that the standard deviation of the sample is roughly the same as the standard deviation of the population. So that's just what I've been talking about. And we talked about that as well in AS. If we are expected to find the confidence interval for the population mean for a large sample, then we usually have the mean and we have a population or sample standard deviation that are already given to us. So here we have an example. We have a telephone company believed that if a customer has not paid their bill, then on average they will owe £100. The company selects at random a sample of size 150, so that means that we've got our large sample there, from those customers who had not paid their bills. The mean amount owed by the customers in this sample was £97.50, and it had a standard deviation of £29. And then we're trying to calculate a 90% confidence interval for the mean amount owed by the customers. So, because we're talking about the mean, if you remember again back to AS, that means that we are going to be having to use central limit theorem. Because we're talking about the mean of the sample, and we're using this to talk about the mean of the overall data as well. So we're finding a 90% confidence interval for the mean. So in order to do this, we're going to go into dist, norm, and we're going to go into inverse normal. So I'm just going to write that down, those steps that I've just taken. So in our statistics function, we go into dist, then norm, and then we go into inverse normal. Now the reason that we do this is because we know what area we're wanting to do. And for confidence intervals, we are always going to have our tail being central. So for confidence intervals, meaning confidence intervals that we're using the normal function for, our tail is always going to be central. So here, I'm going to change this to central by clicking F3. The area is going to be whatever the area of the confidence interval is. So the area, in this case, is going to be 90%. So 0.9. The standard deviation, remember, as I was just saying, because we're talking about the means of the samples, we are going to have to use central limit theorem. So our standard deviation that we put into our calculator is going to be the standard deviation that we have in the question, which, remember, even though that's from our sample, because our sample is sufficiently large, we can assume that that's close to the population standard deviation, divided by the square root of our sample size, which is 150. So that's going to be 29 divided by the square root of 150. And then the mean that we have from our sample is £97.50. So our mean was £97.50. And that gives us our confidence interval here. Now what this actually means, what these numbers here actually mean, is that 90% of the means of the samples that we take, which we can call capital X bar, are going to be between 93.605249 and 101.39475. Now, because this is talking about money, I have wrote everything down there just so I've got my quite accurate answers there. But we are talking about money here, so it'd be quite a good idea to round it to 2 decimal places in this case. That would be the most sensible thing to do. So £93.61 and £101.39. That would be the most sensible way to round it, because as I just said, we are talking about money. So then, if we read the end of our question, so I've done that bit there that I've just highlighted, we're trying to use this to decide if the telephone company's belief is correct or not. Now, their belief is back up here at the top. A telephone company believes that if a customer has not paid their bill, on average, they will owe £100. Now, if we have a look here, £100 is within our confidence interval. So as £100 is within our 90% confidence interval, the telephone company could be correct. Now, the reason why it's only that they could be correct, not that they definitely are correct, is because there's also values that are less than 100. And in fact, 100 is more towards the top end of our 90% confidence interval than it is towards the bottom end of our 90% confidence interval. So the actual mean could be somewhere about 94 or 95, which is quite a bit less than 100. So we can only say that it could be correct because it's within our confidence interval. So we're going to have a look at another example. So it is known that the standard deviation of a certain plant's height is 3.2 centimetres when fully grown. So this is our population standard deviation. Here we are giving it about the population. So then we have a random sample of 35, that's our large sample, of this variety of plant is taken, and the mean of the sample is found to be 134 centimetres. So that's our mean. Find a 95% confidence interval for the heights of this variety of plant. So remember that we are going to be in the same section as we are here. The tail is always central. The area is going to be whatever the confidence interval is. So in this case, it's going to be 0.95. We still have to perform central limit theorem because we're talking about the means of the samples that we are talking about. So we're going to have 3.2 divided by the square root of 35. And our mean is going to be the mean from the sample, which is 134. So as I've just wrote here, my area is 0.95. My standard deviation is going to be 3.2 divided by the square root of 35. And the mean is 134. And remember that what these numbers actually tell us is that 95%, so 95% of the means of the samples that we take are going to be between 132.939858 and 135.060142. And again, here we're talking about centimetres, so I'll round it to the nearest millimetre, so 132.9 to 135.1. So we do have a couple of assumptions that go with this, which is that the sample has to be taken at random. And this applies to our large samples only. When we have small samples, we do have slightly different assumptions, but if we have a large sample, then the only assumption that we have is that the sample has to be randomly taken. And the reason for this is that if our sample that we take is not if it's not a random sample, then that means that our confidence interval is not going to be valid, and actually it could be a lot different. The mean could be nowhere near, the means of the other samples could be nowhere near the actual confidence interval that we have created. So as this is a large sample, there is no need for the population to be normally distributed. And again, we talked about this in central limit theorem in our AS notes. So if you're unsure on why it doesn't have to be normally distributed, have a look back there and hopefully that makes some sense. So I'd now like you to pause the video and I'd like you to give the Now You Try questions a try. Okay, so hopefully you've given the Now You Try question a go. So here we have a plant produces steel sheets whose weights agree known to be normally distributed with a standard deviation of 2.4. So that is our population standard deviation. A random sample of 36 sheets, so that's our large sample, has a mean of 31.4 kilograms. Find a 99% confidence interval for the population mean. So for this one, I put the tail is central, as we do for all confidence intervals. The area is 0.99. Our standard deviation, because we have to use central limit theorem, is 2.4 divided by the square root of 36. And the mean from the sample that we took was 31.4, which means that 99% of the means of our sample will be between those two values there. And you can see them still in my calculator as well. Now this time, because both of the values that were given in the question were rounded to 1 decimal place, I also rounded my answers to 1 decimal place, so 30.4 and 32.4. It may have been 3 significant figures instead that they were rounding to, and obviously our default is still to round to 3 significant figures. If a greater degree of accuracy is needed, then it is always a good idea to write down the whole answers before you perform any rounding in case you round too much. Then in part B, we're asked, would the result be valid if it turned out that the population was not normally distributed? Well, because we have our large sample there, the confidence interval will still be valid as the sample is sufficiently large. So due to central limit theorem, the means of the samples will be normally distributed regardless of the population distribution. And that is the ideal answer that you will give when you're being asked this question. What about if that sample was not random? Well, this would invalidate the confidence interval as the sample must be a random sample. So now I'd like you to try the second now you try question. I think I've managed to fit it all on there, yeah. So now I'd like you to try the second now you try question. Okay, so hopefully you paused the video and gave the now you try question a go. So this time we're trying to find the 95% confidence interval. We have a random sample of 60 tennis balls of the same type and they're bounced, and it's found that the mean is 140 and the standard deviation is 2 centimetres. Remember that this time that standard deviation is a sample standard deviation, but that's fine because our sample is sufficiently large because we have 60 tennis balls. So we're trying to find our 95% confidence interval for the mean height of the bounce. So we've got our tail is central, our area is 0.95, our standard deviation is going to be 2 divided by the square root of 60, and our mean is 140, which means that 95% of our means is between our 139.493939 and 140.506061. And I've rounded that to 2 decimal places. The reason why I decided to go for 2 decimal places this time instead of 3 significant figures is because if I was to round both of these numbers to 3 significant figures, it wouldn't tell me much. I'd only have 139 and 141. Doesn't really give me the same idea of what's going on. Also, giving it to 2 decimal places gave me a good enough look at the difference between the numbers. Might have been able to push to 1 decimal place, but just to make sure, definitely write down the whole numbers before you do any sort of rounding. So then on this second part here, we have a random sample of 50 of a second type of tennis balls. This is different from the first set that we were just looking at. It's taken, and the mean heights of the bounces of those balls is 141 centimetres with a standard deviation of 1.5. Again, that is a sample standard deviation, but that's okay because we still have a sufficiently large sample of 50. The experimenter believes that this ball has superior bouncing power. So we're hoping that this ball's confidence interval is going to be higher than the previous ball's confidence interval. So find a 95% confidence interval for the mean height of the bounce of the ball of this type, and we're trying to comment on the experimenter's claim. So this time, again, our tail is central, our area is 0.95. This time our standard deviation is 1.5 divided by the square root of 50 because that was our sample size, and the mean is 141. And that means that 95% of the means for the second type of ball are going to be between 140.584229 and 141.415771. And again, I've rounded those to 2 decimal places, and we can see the difference there. Now, if we compare this confidence interval that we've just drawn here, so this one here, with the confidence interval from the previous ball, which is this one here, we can see that the highest bound of the first ball is below the lower bound of the second ball, which means that the experimenter is probably correct that the second ball has a higher bounce than the first ball. However, as always in statistics, we can only say probably, not that they are definitely correct. So as the 95% confidence interval for the second ball is above that of the first ball, the experimenter is probably correct. Now, as I said before, there were three different categories that we had in terms of normal confidence intervals. If I just flick back to that. Sorry, back again. That's this part here where we have the table. So far we have looked at this one here and this one here. So we've had a look at examples where we have a large sample and we have a known standard deviation, and we've had a look at those where we have a large sample and we have an unknown standard deviation. We are quickly now going to have a look at a small sample and a known standard deviation, because this is the last category where we do our confidence intervals in this same way. So, if we are using a small amount of data, then it does matter whether we have been given the population or the sample standard deviation. If we are expected to find a confidence interval for the population mean for a small sample, then usually we will be given the mean of the sample, but in this instance we will be given the standard deviation of the population, which must be used to find the confidence interval. So sometimes we could have to find the mean, but we will be given the population standard deviation. So we'll have a look at what that looks like. So here we are told we have a factory that produces jars of jam. In each batch of jam, the weights are known to be normally distributed with a standard deviation of 7 grams. So that is the population standard deviation. And then we have a sample here. This time we're not given the mean of the sample, but we can find that using our graphical calculator. So if I click exit to go back into my statistics function, just as we did in AS, we simply type those values into our calculator into list 1. So 481, 455, 468, 457, 463, 469 and 458. As always, double check that you've definitely typed those values correctly into your calculator. And there I have 1, 2, 3, 4, 5, 6, 7, 8. And I have 7 values there. I've missed one out. 1 second, sorry. 68, 57. I've missed 469. Now it doesn't matter which order you type the numbers in, so I can just type in the one that I missed at the end. So then we're going to calc, set, and because we don't have any frequencies, we want our 1 var X list to say list 1, and we want our 1 var frequencies to just say 1, because remember that tells us that we don't have any frequencies. Then we go to 1 var, and it's this first value that we're wanting to look at. So the mean from our sample is 465. And as I just said, the N is 8. So now we do things the same as we did when we had our large sample. So we go into dist, norm, inverse normal. Our tail should always say central still. Our area is going to be the area of our confidence interval. Our standard deviation is going to be that of the population divided by the square root of the sample size. And our mean is now going to be the mean from the sample that we have taken. So we've got 7 divided by the square root of 8. And we have 465. So that tells us that 95% of the means of our sample are going to lie between 460.149337 and 469.850663. And again, once you've wrote down all that values, you could do some rounding. So you could say between 460 and 470 in this case. rounding to 3 significant figures in the same way as the values were given to us in the question, as long as you definitely have the entire confidence intervals there as well. So the manager of the factory claims that the mean weight of the jars is 454 grams. Is he right? Well, if we have a look here, we can see that 454 is definitely below our 95% confidence intervals. So actually, the manager is probably incorrect. As 454 grams is below the lower bound of our 95% confidence interval. So what is the probability that the mean does not lie within the confidence interval? Well, because here we're talking about the mean, not the mean of a sample, we can't really say, because here we're talking about what is the probability that the mean, not the mean of a sample, but the actual mean of our population. Now, because we don't have a lot of information about our population, we cannot say whether it lies within our confidence interval or not already. We can't say what probability it is that it doesn't lie within our confidence interval. So if this was the mean of a sample, then the chance that it doesn't lie within it is just going to be 5%, because as I said, 95% of the mean should lie within that confidence interval. But because we're talking about the actual mean of the population, we cannot say whether the mean of the population lies within the confidence interval or not. And as I just said, just as a side note, so note the probability that the mean of a sample does not lie within the confidence interval is 5%. And the reason why it's 5% is because we had a 95% confidence interval, which means that there's only a 5% chance that a mean of a sample does not lie within the confidence interval. So that slight difference between the wording gives us a completely different answer. So in part C, it's actually asking what the probability that the mean of the population doesn't lie within our confidence interval is. Now, the mean of the population is either going to be in the confidence interval or not in the confidence interval, because the mean of the population is not going to change. It is a set value, so it is either in there or it's not in there. Whereas the mean of a sample is going to be different depending on what values are taken in the sample. So we can say that there's a 5% chance that the mean of a sample doesn't lie within the confidence interval. And that is true for any confidence interval that we take. So that point that I've just made on C is true regardless of whether it's a large sample or even T when we get onto that. So having a look at the second example, we have a soft drink machine is regulated so that the amount is delivered per cup is approximately normally distributed with a standard deviation of 1.2 millilitres. the amount delivered in millilitres to 5 cups, and we have our values here. And we're just trying to find the 90% confidence interval for the mean amount that is delivered per cup by the machine. So again, our tail is going to be central. Our area is going to be, this time, 0.9 because we're looking at a 90% confidence interval. Our standard deviation, remember that 1.2 is the standard deviation of the population, divided by the square root of our sample size because we have to use central limit theorem. And for our mean, we need to find the mean of these 5 numbers. So again, we're going to type those into list 1 in our calculator. So 212.6, 210.4, 211.5, 209.8 and 210.7. Just a quick check that we have typed all of those in correctly. Then we're going into calc. I did check this for the last one, but remember that it needs to say list 1. We have no frequencies. And then we go into 1 var. And we can see there that our mean is 211. So we're going into dist, norm, inverse normal, central, 0.9, 1.2, divided by square root of 5 and 211. And that gives us that 90% this time of the means of our samples lie between 210.117279 and 211.882721. All these values here have been given to 1 decimal place, so I'm going to give my answers here at the bottom to 1 decimal place, so 210.1 and 211.9. So just a little bit on the assumptions that go with this. In the same way as we had for our large samples, the samples that we take must be a random sample. And this time, because our sample is not sufficiently large, that means that the population must be normally distributed in order for this hypothesis test, this confidence interval, to work. Okay, so because we have a small sample, that means that the population has to be normally distributed, and that's because of central limit theorem. So I'd now like you to pause the video and give the 2 now you try questions a go. Okay, so hopefully you paused the video and you gave the 2 now you try questions a go. So for this first one, we have, after a particular wet night, 12 worms surfaced on a lawn. Their lengths were measured in centimetres, and we have the lengths there of our 12 worms. Assuming that the population came from a normal population with variance of 4, so we need to be careful there that the population variance is 4, which means that the population standard deviation is going to be 2. Again, that is from AS, that the variance is the standard deviation squared. So in order to get the standard deviation, we are going to have to square root it. Calculate a 95% confidence interval for the mean length of all worms in the garden. State any assumptions that you have made. Well, we've been told already to assume that it's from a normal population. So looking at our 2 assumptions at the top, we are having to assume that the sample is a random sample. When we put those numbers into our calculator, we end up with a mean of 10.3916666. And as you can see with what I've wrote below, I typed that whole number into my calculator. I didn't round it at this stage, and the reason for that being is that if I round the mean now, then my confidence interval is going to be slightly different, and because I don't want to have that discrepancy, I'm going to keep my mean to as many significant figures as I can, and only round when I actually have my confidence interval. So the tail was central, the area was 0.95 because that's the confidence interval that we were finding. The standard deviation for the population was 2, as we said, the square root of 4, divided by the square root of 12 because of central limit theorem, and the mean is that 10.391666. So that means that 95% of our means are going to be between 9.26008087 and 11.52322523. And here I decided to stick with the rounding to 3 significant figures. As I've always said, unless it states otherwise, stick to 3 significant figures. If it does say use a suitable rounding, then you have to do what I was doing in the other questions, having to think about what our units are, having to think about what kind of level of accuracy was given in the question. Those sort of things you need to get used to having a look at. So that's why I had a look at those in the previous question in case that part does come up. In the second Now You Try, we have a lot of numbers here, okay? But the numbers are in a way just to reassure us. So we have a piece of apparatus used by chemists to determine the weight of impurity in a chemical is known to give readings that are approximately normally distributed with a standard deviation of 3.2 mg per 100 grams of the chemical. So there it's telling us how much of the chemical we need in order for the standard deviation to be 3.2. So in order to estimate the amount of impurity in a certain batch of the chemical, the chemists take 12 samples, each of 100 grams. So again, it's just saying that because the 3.2 per 100 grams was our standard deviation, and here we are still taking the 100 grams, it's just saying we're still taking the same amount really. From the batch, and measures the amount of impurity in each sample. So the results obtained in milligrams per 100 grams are as follow. So again, the fact that it keeps talking about this 100 grams is just trying to reassure us we are looking at the same amount of the chemical. We're not having to try and do any conversions or anything like that. We are looking at the same amount. We know the standard deviation for the 100 grams, and then we keep having a look at 100 grams. So that's good. So as I said, the standard deviation is 3.2. Our sample size is 12, and then when we put all those numbers into our calculator, we get 7.75 for the mean from that sample. So again, in dist, norm, inverse, normal, we have our tail being central, our area is 0.9 because that's our confidence interval, our standard deviation is going to be 3.2, which was the standard deviation of the population divided by the square root of 12, and our mean is 7.75, which means that 95% of the means of our samples are going to be between 6.23054931 and 9.2694569. And again, you can see there that I've rounded them to 3 significant figures as well. Now you'll also notice that I have put a little comment there saying assuming that the samples that we are taking are a random sample. I should say is a random sample. And the reason why I just added that there is because nowhere in that does it say that the samples are random. It just says, in order to estimate the amount of impurity in a certain batch of the chemical, a chemist takes 12 samples, each of 100 grams from a batch. It doesn't say that the samples were taken randomly. So it is quite important that we do check that, because sometimes we are needing to add an assumption in there, even if it doesn't necessarily state an assumption. And sometimes that can be a later on part saying, what assumption do we need to in order to make this test valid? So just make sure that when you're reading the question, especially for these confidence interval ones, if it's a large sample, that it states that it is a random sample, and if it's a small sample, and we know the population standard deviation, then we need the population to be normally distributed, and we need the sample to be a random sample still. Thank you very much for listening, and next time we're going to go on to looking at a small sample with an unknown standard deviation.